start. One moment here. All right. So, if you haven't looked at the chain rule assignment yet, you probably don't want to put it off until Friday when it's due. So you want to try to get a look at that a little ahead of time. That way, if you get stuck, we can try to sort some of that out. Just if you remember some of them, the answers get kind of ugly and things like that. So there's my pitch for you to not procrastinate on that one, especially. Okay, let's see. So we have another one of those sections where we don't have a lot of slides, so then we'll be mainly doing examples. We're gonna talk about a slightly different way we can find the derivative, called implicit differentiation. And then also in this section we get thrown in, because we need implicit differentiation to really be able to get to the definition, we also throw in the derivatives of the inverse trig functions. Okay, so we have kind of a two-part section here. So to get the idea of what we mean by implicit differentiation, we can think about functions like we've been dealing with, like y equals square root of x cubed plus 1, or y equals x times sine x. Those functions, we would say they are explicitly defined. Okay, they're defined in a way where we can write down y equals something, and then we get our function in that. And in those cases, we can also say y is the same thing as f of x, so we can say f of x equals whatever it comes after that. Okay. If you look at these next two, we've got two equations here. Don't really want to call them functions exactly. And we've got two equations here where we are not explicitly solved for y or x. We're not explicitly solved for either variable. And sometimes we have equations like that where we still need to know things about the derivative. And this idea of implicit differentiation is going to give us one way to come up with that. If we look at the first one, x squared plus y squared equals 25. You might know what that's the equation for if you think about the graph of that. What's it going to look like? Ringing a bell there? X squared plus y squared equals 25. What will that be? I got it here. So that's a circle. A circle with a radius 5, square root of 25. And since we don't have anything added to the x or to the y, our center is at 0. So this thing implicitly actually gives us more than a function. Because looking at the graph, we have a circle. You notice anything if we're thinking about functions? You notice anything about the graph of a circle? Would that be a function? Let me ask you that. Yeah, so it doesn't pass the vertical line test, right? We have a ton of places where we could draw in a vertical line, and it would fail the vertical line test. So written exactly like that, x squared plus y squared equals 25. It's not a function. It's not a function. Second one we had here was x cubed plus y cubed equals 6xy. That one, if we look at the graph, you probably don't know that one. It's okay. If we look at the graph there, sorry, wrong place here. Get this one, this graph. It's called the Folium of Descartes. So again, if we think about this graph and think about is it a function, it would not be. It would not be because we've got places where we could draw a vertical line, it would touch more than once. In fact, we've got some places where it would touch 3 times. And so this would not be a function the way it's written. But what we actually have extra information. We'll come back to these. We actually have extra information given to us. It turns out that this first one's not too bad if we want to solve it explicitly. So we want to make it be y equals something. You could do x equals. Typically, we solve for y as our dependent variable. Okay, but we could solve x squared plus y squared equals 25 pretty easily, and we'll look at that in just a second. The second one is not so easy. It is solvable. Okay, we could write equation 2 down there, that folium picture. We could write it down as y equals something. It is pretty ugly. And I'll show it to you here in a second. It's pretty ugly though. Okay. So let's look at the circle one first. Okay. So if we take in, let's look at what we're doing real quick. So we had x squared plus y squared equals 25. So how would we get there? The text just kind of assumes we see how to get there. So we could subtract x squared from both sides. And then to get to y, we would need to take the square root. But when we do that, what do we have to remember? We're going to take the square root of both sides. We need to remember plus and minus. So we would get 2 expressions actually. We get 2 things. We would get positive square root of 25 minus x squared and negative square root of 25 minus x squared. It turns out that each one of those is a function. So written in implicit form, we're actually given the definition of 2 functions in one equation. And even though this is the way it works out algebraically, you could actually think about it as maybe more than 2. So if we think about those pieces, we got positive square root of 25 minus x squared and then negative square root of 25 minus x squared. If we think about those graphs, the positive root, positive radical, gives us the top semicircle, and the negative gives us the bottom semicircle there with that radius. And so if you check these with the vertical line test, they would both pass. Now we get rid of our problem of failing the vertical line test there. So one option we have on this equation is that we could solve it for y. We would get 2 functions, and then we could use the rules we've already worked up so far to come up with the derivatives. Okay. But then what do we do with things like number 2, where it's not so easy to solve for y? Let me go ahead and show you that. So that one, x cubed plus y cubed equals 6xy. Let me pull it up here. So here's our equation. If, okay, there's actually, not squared, that's cubed, sorry. So there are actually, you know how we have the quadratic formula where we can get the general solution to a quadratic equation, our exponent is 2. There are actually general solutions to cubic equations. They're really messy. Okay. And if you solve this thing with like some kind of software to do those general solutions to the cubic equation, here's what we would get for this one. move it down. I'll make it a little bit bigger so you can see it. So there would be our 3 solutions to that. So here's one solution. You got those radicals under a radical, square root under square root, and then our other 2 come from here because we have a plus minus there. That would be our general solutions to that one. So solving for the general solution there, solving them explicitly, at least to me, doesn't look like it makes finding the derivative easier. Okay. I think this implicit technique we're going to use is going to be better than having to first to get to all this and then find the derivative from there. Okay. So there's a little bit of motivation. Okay. And this thing looks so unassuming too. Right? Just x cubed plus y cubed equals 6xy. Doesn't look that terrible, but turns out to be pretty messy. So here's our idea. We look at the folium. Those 3 solutions we saw, okay, are actually these parts of the graph. So we've got this portion, and this portion. So all 3 of these individually would pass the vertical line test. Okay, so here's the idea. Okay. If we solve one of these things explicitly, and what we're doing is we're saying here's y, and it is this function of variable x defined this way. The alternative is just to keep in mind that y can be considered as a function of x. Okay? That if we did solve for y, and then we could write it out as you'd have a function of x there. So keeping that in mind that we could write y in terms of x, we're going to have this idea of implicit differentiation. Okay? And all we're doing, okay, is we're thinking about y as a function of x itself. Okay? So then when we take the derivative of something that has a y term, okay, we're going to have to use a chain rule. So let's look at one. It's not that bad. Let's look at this one. We're going to use our circle equation, x squared plus y squared equals 25. We want to find dy dx, so the derivative of y with respect to x. Okay. We're going to keep in mind that we're treating y as its own function of x. Okay. So let's go over to our scratch paper here, and we'll do that where we have plenty of room. Okay, so we want to find y prime given x squared plus y squared equals 25. Okay. So again, one method, we could solve it for y and then find the derivative there. But we're going to look at how to do it without solving it for y. So I said y prime. I think it's easier to think about if we think about dy dx forever. Same meaning, different notation. We want the derivative of y with respect to x. Okay. So what we're going to do is we're going to just take the derivative of both sides. Take the derivative of both sides. So on the text, we'll write it down. You don't have to write this every time. We're just kind of, this is our first one, so we're keeping track of what we're doing. We would find dy dx of both sides here. Okay. And so on the left, the way we would find the derivative of that side, we have a sum. Okay, the way we would find that derivative is we would find dy dx of the first term, x squared, plus dy dx of the second term, y squared. And then, no big deal on the right, we just have the one term. So with the first term, I got x squared, and we want to take the derivative. That's not really any different than anything we've been doing. I think we're just taking the derivative of something with an x. Okay, so we can use our regular derivative rules. So if we wanted the derivative of 2x, what's that going to be? I mean, derivative of x squared, what's that going to be? 2x, yeah, 2x. Only 2x. Okay? So that's business as usual. Where we run into a little difference is when we're taking the derivative of a y. Okay? Because we're thinking of y as a function of x. Okay? So it's like we're thinking about, we've got this outer function of a square, and then our inner function is whatever y is. Okay? So we're using chain rule, is what we're doing here. So if we wanted the derivative of the y squared part, the square, that would just be 2 times our inner function here, which is y, and then times the derivative of the inner function, which is y. So the derivative of our inner function we could call y prime, or you could say dy dx. I'm kind of mixing notations here for clarity. Yep. Yep. Sure will. Sure will. Okay. And then the other side's easy, luckily. Okay. Yeah, because we're taking the derivative of a constant, so it's 0. Just 0. 0. Right. So keep in mind what we're trying to find. We're trying to find dy dx or y prime, and whichever notation we're using. And so here's an equation we've ended up with by taking the derivative of both sides, and we're trying to solve for this thing. Okay? And solve for that. So now it's just an algebra problem. Okay? We're trying to solve for y prime. So first thing we could do, we could subtract 2x from both sides. Trying to get y prime by itself, or dy dx, whichever one you want to use. Then on the left side we have 2 times y prime. We're trying to end up with just y prime by itself. So back to just basic algebra rules, what should we do? Divide it by 2y. Those 2's and y's, those cancel. So we have y prime, or dy dx if you prefer, equals negative 2x over 2y. The 2's can cancel. You should get negative x over y. Okay, so you could, again, this could be dy dx. So there is our derivative. Okay. One thing that's a little bit different when we find a derivative implicitly, okay, sometimes we end up with an expression in terms of x and of y. Okay. If we're finding an explicit derivative, we usually just have x in there. So here we have an x and a y involved in our derivative. That's okay. Let's look at part 2. Part B says find the equation of the tangent line at the point 3, 4. Okay. So part B, we want the equation of tangent line and what was the point? 3, 4? Yeah, 3, 4. Okay, weird comma. 3, 4. Okay, so we have the derivative. Remember what the derivative gives us. The derivative gives us the slope of the tangent line at whatever values we plug in. So we need the slope of the tangent line at 3, 4. It's not a big deal that we need x and y, because here we've got a point that has an x coordinate and a y coordinate. So here, y prime, the slope of our tangent line would be negative 3 over 4. That's the slope. That's the part we worked so hard for. And then to get the equation of the tangent line, it would be y minus our y coordinate. That equals our slope, negative 3/4. X minus our x coordinate, which is 3. So there's our equation. If we want to, we can solve it for y. Let's see, minus 4 would be minus 16 over 4. So negative 3/4 x minus 7 over 4. There's our tangent line. I should have added it, you're right, because I subtracted it. It's a plus, so then it makes it 25 over 4. Thank you for catching that. Okay. So let's look. Okay. We got negative 3/4 x plus 25 over 4. Let's check it on the graph. So go back to our circle and then put in our, it was negative, wasn't it? Nope. X plus 25 over 4. And we wanted that to be tangent at the point 3, 4. There. Keep forgetting what our point is. Yeah, 3, 4. So look at there. We got it. So there's our point. And we had our circle, our point, and we got our tangent line. Not too bad. The thing that's kind of interesting about this is that if we move down to 3, -4, we will get a different slope. But we've got this one little expression, this negative x over y, that's giving us the slope of the tangent line for two different functions. We've got the function that's the upper semicircle and then the function that's the lower semicircle, but we can use the same expression to get the slope of the tangent line for both of those. So nice. If you go through the process and you solve the equation of the circle for y and you get two different functions, you would have to use the appropriate one depending on where your point was. So you'd have two different expressions for slope. In order for it to work out correctly, you'd have to plug into the proper one. The implicit version doesn't care. It's going to give you the slope for any of it. There's that one. What about the other one? What about our other equation here? Where is it at? all the way back here. So what about x cubed plus y cubed equals 6xy? Well, if we want dy dx for that one. Okay. Let's PowerPoint froze up on me. Hang on 1 second here. Sometimes I unplug from the projector and then plug back in. It'll fix it. So let's do that one. On this one, we've got x cubed plus y cubed. Is that how I have it written? Yeah, x cubed first and then y cubed. So there's our implicit expression. Like I said, this one really defines three different functions at least. Maybe we can write it as 3 different functions. So we want to find dy dx. Yeah. Technology is not cooperating up here. Want to find dy dx. Then we can just go term by term, taking the derivative, but just remembering anytime we take the derivative of something with a y involved, we're thinking about it y as a function of x, so we have to use the chain rule. So for the x cubed term, there's no y involved there, so it's just business as usual. So we want dy dx of x cubed. What's that going to be? 3x squared. Okay. And then we want dy dx of y cubed. There we start off the same way. We'll have 3y squared, but then we're thinking about y as a function of x, so we'll have to multiply by the derivative of y with respect to x. So either you can write y prime, or you can write dy dx if you prefer. And maybe I'll use dy dx on this one just to do one with both. Okay. Slightly more writing, so I don't mind it. Okay, so there's our left side taken care of. The right side, what are we going to have to use to find our derivative on that one? Chain rule, yeah, for the y part, but we got something else involved. We got product rule, because we have, depending on how you think about it, and it doesn't matter how you think about it. You can either think about it as we have like 6 times x times y, or you can think about we have 6x times y, or you can think about we have x times 6y. One thing about it that way. Since it's commutative, we can get away with thinking about it whatever's most convenient. Hang on, the way I like to think about this one is I like to think about it as 6x times y. Then when we do product rule, okay, I have the order I do it in. I have the derivative of the first term, so that's 6, times the second term, that's y, plus the first term, which is 6x, times the derivative of y, which is just 1, but it's 1 times the derivative of y, right? So it's, we get a, let me back up. Let me write down exactly what we're doing. So we got that times y plus 6x times derivative of y is 1, but then we have to use chain rule, so we'll have dy dx. Yep, you got chain, yeah. Okay. Then I'm just gonna simplify my right side a little bit, and then we'll deal with it. So 6y plus 6x dy dx. So one benefit of using dy dx instead of y prime is it's not as easy to lose in there. If you miss one little tick mark on the y prime, you can kind of disappears in there and you lose track of it. Okay. So we're trying to solve for dy dx, or y prime if you use that notation. So the first thing we need to do at this point is just algebra. We just have a weird looking dy dx term in there. Okay. But we need to get everything with a dy dx on one side, get everything else on the other side. That's going to be our first goal. So on the left, I'm going to subtract 6x dy dx from both sides. And so I'm taking this one and moving it over. Okay. And then on the other side, we're going to subtract 3x squared. So subtract it from both sides. So this one's moving over here. Just two moves there. Okay. And then what can we do from here? Nothing. No idea. Trying to get dy dx by itself. Getting there. We're getting there. Right now, yeah, you got the right thing in mind. So ideally, right, we want this 3y squared to get moved over here. We want this negative 6 to get moved over here. But right now, the problem is if we try to divide by one of those, then it makes the other one more complicated. We've got one step before we can do that cleanly, and that's that we have a common factor of dy dx. Right, that's in both terms. So we factor out a dy dx. That's right. So we'll have dy dx times 3y squared minus 6x is equals 6y minus 3x squared. Now we can divide by what we've got left in the parentheses. So we can divide by 3y squared minus 6x on the left. That'll leave us dy dx. There we go. If we want to, we can simplify a little bit. Not strictly necessary. Depends on what we're going to do with this thing. But one thing we can do is we have a common factor of 3. We can factor out the top and of the bottom. Then we can cancel those. So final answer for me will have 2y minus x squared over y squared minus 2x. So that would be dy dx. And again, since we found this thing implicitly, we end up with something that involves x and y. That's okay. Where that comes into play is it's like we have to know x and y to figure out which piece of our graph we would be on. Let's look at the folium again. So we would need, like we would have to have x and a y coordinate to know, like, are we on this piece, or are we on this piece, or on this piece, or on this piece. So we could plug in the point where we wanted to know the tangent line, and have x and y, get the slope of the tangent line there. And then we could put it in point slope form if we wanted the equation of the tangent. But this thing we ended up with, it actually gives us the derivative of multiple functions, because the thing we started with, the x cubed plus y cubed equals 6xy, actually defines multiple functions in one equation. All right, that's going to be what we used there, where we got all the derivative terms on one side and then factored out so we can divide. That's going to be pretty common. That comes up on a lot of these. That's where we're at. All right, there's that. Let's see. Okay, so looking at the graphs, we've seen two implicitly defined expressions. Right? We had the circle, that gives us two functions, the upper semicircle and the lower semicircle. And we've got the folium, and it gives us at least three, depending on how you count it. And really messy general solutions, if you want to think about those. They can be a lot more complicated. This next one is an implicit expression. And you can see probably that it's something where we would have trouble solving for y. We've got cosine of x minus sine y equals sine of y minus sine x. So I don't know of any method we could use to solve that explicitly for y. And we probably wouldn't want to if we could, because we would probably end up with a bunch of solutions, because here's our graph. Okay. So, a lot of functions that we could come up with taking different pieces of that graph. It is periodic. If you zoom out, it looks pretty cool too. Any pieces of that you pick out where they pass the vertical line test, that would be a function. So we actually have a bunch of different functions defined there. Okay. And then this last one, let me zoom in a little bit. This last one looks so innocent. Sine of x times y equals sine of x plus sine of y. Desmos even has a little trouble with this one. There's a pretty interesting looking graph there. Okay. So any pieces of that you pick out where it passes the vertical line test, then you get a function. A bunch of those involved there. Okay. So that thing, just looking at the graph, I would not want to, even if it was possible, I would not want to solve that for y. Okay. But looking at the implicit definition here, that would really not be too bad to find the derivative implicitly there. And we would have product rule inside a sign, and then no big deal on the right side. Not that bad. So implicit differentiation, it can be really nice. It can save you a ton of trouble. We're trying to find derivatives for these functions where they're hard to solve explicitly. And then there are plenty of functions out there where we cannot solve them explicitly. So implicit differentiation is really our only option on those. And we're going to do some more examples, but when we get to the other half of our topic today, we kind of get thrown together here. Derivatives of inverse trig functions. So we're not going to go into a ton of the details with these. And then the main thing is just we're going to look at the formulas. Okay, we're going to look at the formulas for the derivatives. Okay. But okay, there's a couple of things to point out here. So two ways you can write inverse trig functions. Okay. To me, the better way is going out of style. Okay. To me, the better way of talking about the inverse sine function is calling it arc sine. Okay. You can also write it sine inverse. Okay. Those mean the same thing. Okay. So arc sine of x is the same thing as that, minus 1. Those mean the same thing. And if you put arc in front of the other trig functions, it means the same thing. Unfortunately, that notation is kind of getting left behind, and it's kind of old-fashioned, calling them the arc functions in place of the -1 notation there. Okay. Well, let's look at this. Okay, we're trying to find the derivative of the inverse sine function. Okay. Then saying y equals the inverse sine of x means that sine of y equals x. And then we got our domain over here. So if we take the derivative of both sides in this form, we would have cosine of y and then dy dx using the chain rule. And then taking the derivative of x, we would just get 1. If we rearrange that, we get dy dx is 1 over cosine y. And then because of our domain, we get this. All right, so cosine of y, we got 1 minus sine squared y, where we're playing with this arrangement here. We get 1 minus x squared. You don't have to be able to derive it. Okay. Just want you to kind of see where they come from a little bit. So here's our first one. Okay. Here's our first one. That if we want the derivative of sine inverse, I get 1 over square root of 1 minus x squared. They just look like they come out of nowhere if you don't see any of the process of how you get there. And then tangent inverse is another one that comes up fairly often, and we won't worry about the whole process there, but here's where we end up. So we need implicit differentiation to be able to derive these, so that's why they get thrown in this section. These I do not have memorized, okay, so I don't really expect you to have them all memorized either. But let's use these two we've talked about. Okay. So first one is let's find the derivative. We have 1 over inverse sine of x. Okay, so let's go to our scratch paper. So we have 1 over inverse sine of x. Okay. So we had our definition, right? Let me write it back down. Our definition said ddx sine inverse of x 1 over square root of 1 minus x squared. Sorry, it's a little sloppy. cut on the edge of the screen there. Okay. So we want our derivative here, so we're calling this y, right? Yeah. So one thing we can do, we can move inverse sign up to the top, just a rewrite. And then when we go to find dy dx, we can use chain rule. So the outer portion there would multiply -1 in front, leave the inside alone, subtract 1 from the exponent, and then times the derivative of the inside part. So the derivative of our inside part is 1 over square root of 1 minus x squared. Okay. Then that's it. That's our derivative, but then we need to clean it up a little bit maybe. So we could put a minus sign out in front of the whole thing. We'll have a 1 on the top, and on the bottom we'll have sine inverse squared. Makes it positive when we move it to the bottom, and then square root of 1 minus x squared. So it's not pretty, but that's what we end up with. Questions on what happened on any of that? It's kind of messy, so it can be kind of hard to follow. Okay. Do one more. I didn't give you many of these. They're just applying, writing down the rules. So let's see, part B. Wants us to find the derivative of f of x, where f of x is x times arctangent square root of x. Arctangent, that is just an alternative notation. That same thing. So really here we have two terms. Right? We got x times arctangent of square root of x. And then I'll put our definition over here again. So that one was 1 over 1 plus x squared when we need it. Okay. So since we have these two things multiplied together, we've got to use product rule. The product rule. So f prime take the derivative of the first one, it's 1, times the second one, which is just arctan of square root of x, plus first one, so x, times the derivative of the second one. Is where this one gets a little messy, because not only are we dealing with arctangent, but it's not just arctangent of x, it's arctangent of the square root of x, so we have chain rule involved here. Okay. So fun times. Right? So we could rewrite this, x to the 1/2. We don't need parentheses. Right? So then we're filling into our inverse tangent derivative. But pay attention that this is x, so we end up with x squared. When we use it here, we're going to have x to the 1/2. So when we square x to the 1/2, we're just going to get x. So for the inverse tangent part, we'll have 1 over 1 plus x to the 1/2 squared. And then we have to do times the derivative of our inside function, which was x to the 1/2, so times 1/2 x to the negative 1/2. So if you wanted to find an ugly derivative today, there's one. Okay. So if we clean that up a little bit, let's see, that is arctangent square root of x plus, let's see, we have x on the top, and then 1 plus x on the bottom, and then that's times 1 over 2 square root of x. So altogether, x over 2 root x times 1 plus x. So, not pretty. There, hang on. Is that right? I think the textbook's got a typo on their answer on this one. Yeah. So this part, 1/2. Yeah, that's right. So the textbook actually has the square root of x up here, but it's got to be negative. Right? It's -1. I think we're good there. Unless I did something dumb that I don't see. It's kind of tedious. We don't have a lot of those we're going to have to do, so don't panic. Okay, but here's the full list. And so if you're keeping track somewhere of all the derivative rules we've got, here's the list of the 6 inverse trig functions. And again, you could call them arcsine, arccosine, arctangent, arccosecant, arcsecant, arccotangent. Mean the same thing. No, these 6 you don't have to remember. As long as you can do these 6 with a reference to the formula, you're okay. There's probably, so sine, cosine, inverse sine, inverse cosine, inverse tangent are not too bad as long as you remember one of them. If you can remember inverse sine, then the cosine, you have just a minus sign. And then when you have tangent, you get rid of the square root, so that's not that bad. But I start forgetting, like on these, which one has x and all that stuff. I'm not going to make you remember it. we've got enough to remember. So. You got which one of those? Still writing. I'll let you write. And then we'll do a couple more implicit examples. So the thing that, while you're finishing writing that up, the thing that I don't like about calling it this is it looks like that should be like when we had a problem like we just had. When we have that, it looks like that should be sin x, but it's not. It's not. It's not. So that's why I don't like that notation. You'll see it both ways. Okay, you'll see it both ways. Got those? All right, so let's look at a couple more here. And here we want to find y prime and sine of x plus y equals y squared cosine x. We don't have any way we can solve for y here. This one we can't do explicitly even if we wanted to. So implicit differentiation is our only option. So on the left side, when we go to take the derivative, what are we going to have to use? What rule? Chain rule, because we've got x plus y inside of sine. Okay. And then on the right side, what do we have to use? Product rule, because we have y squared times cosine of x. Okay. So we've got quite a mix on this one. Okay. So taking the derivative of the left side, the derivative of sine of x plus y, the derivative of the outer portion, the derivative of sine is cosine. We'll have cosine of x plus y times. Now we need to take the derivative of x plus y. So the derivative of x, what's that? It's just 1. And then plus the derivative of y, that would be 1. But then we need times y prime or dy dx, whichever notation you want to use. Okay. That's our left side. On the right side, we got product rule, so the order I do it in, I'm going to take the derivative of y squared, so that'll be 2y times dy dx, or y prime, times the second function, plus first function times the derivative of the second function, so the derivative of cosine x, negative sine x. Okay. So, as long as you're careful, that part's not all too terrible. You do have to remember the y prime part, since we're doing implicit. Then we want to solve this thing for y prime. So the algebra, Get a little messy here. I think probably what we need to do is I think we probably need to distribute this cosine x plus y. Not too bad since these are one coefficients and on the left. You may be able to do it another way. That's just how it looks to me. So let's see. So that would be cosine x plus y times 1 is just cosine x plus y, x plus y, and then plus we've got a y prime, so y prime cosine x plus y. I'm doing that because I know I'm going to want to get the y primes on one side by themselves. So then on the right side, just to clean it up a little bit, that's 2y y prime cosine x minus y squared sine x. I'm going to take the 2y y prime cosine x and subtract it from both sides. And then I'm going to take the cosine xy, ooh, I need another color, the cosine xy, subtract it from both sides so it moves over. So, got a little crazy there. So let's see, I'll have negative 2y y prime cosine x plus y prime cosine x plus y equals negative y squared sine x minus cosine x plus y. This is when you hope you've got plenty of paper laying around. That's the worst of it. We're almost there. What's left? Trying to solve for y prime. Factor out a y prime on the left. Yeah, so we'll have y prime times negative 2y cosine x plus cosine of x plus y equals all this messy stuff on the right side. And then one last step. Divide by all the junk we've got in parentheses, yeah, so y prime equals negative y squared sine x minus cosine x plus y over negative 2y cosine x plus cosine of x plus y. Okay. And, there may be, okay, so no, I don't, never mind, I started to say I see something we can do, I don't see it. There may be some simplification you can do, but that's fine. That's a little bit of a pain to have to type in the WebAssign, but you get there. So somehow what it's supposed to come out, I think it looks like I've got a negative 1 canceled is all, so you could do that. Okay, you could factor out a negative 1 from the top to make both these positive, and then it would switch the signs on the bottom and cancel it. That's equivalent. So we're good there. Messy answer, and believe it or not, I tried to pick out the least messy answer ones on WebAssign for the assignment because some of them are just ridiculous. Some of them come out with at least twice as much stuff to have to type in, and I know that's annoying. So. Questions on that one? You track along, okay? Let's do one more. It's not, we don't have trig involved in it at least, so. But we do have another kind of thing to take into consideration thrown at us. And you only have one of these in the assignment, but it says find the second derivative. Okay. Yeah, let's say when. Just so we can say we know how to do it. We've got one where we need to find the second derivative implicitly. Well, so let's think about that. We would have y to the fourth equals 16 minus x to the fourth. Okay. And then if we would have to take fourth root there, so fourth, and then, yeah, maybe. Seems plausible. Oh, plus or minus. Yeah, I forgot plus or minus. The issue, though, then is, so that would be y prime. Well, that would be y, we can find y prime. And then the issue there, though, then is we have to find y double prime. And so here we get 2, so we would have 2 different derivatives, and then we would have 2 different expressions for the second derivative. So it's kind of messy that way. This is not too bad. This is not too bad. So good thought. Good thought. Anybody know what this graph looks like? No, it's not bad. Okay? So what does that equation look kind of like? It looks kind of like the equation for the circle. Yeah, we just have different exponents, right? We got to the fourth power something there. So it won't take but a second. Let's look at it real quick. No, that would be cool though. Yeah, come on, Wi-Fi. Yeah, so we got x to the fourth plus y to the fourth. Oh, not plus. Equals 16. It probably has a formal name. It's kind of like a square, but we rounded off corner. I'm sure it has some formal name based on some kind of Latin root, something out there. But informal name called a fat circle. Kind of neat. And then just as a side note, all that happens if you increase the exponents here. Yeah, you gotta make a match. Hang on. Increase the exponents here. Well, maybe it gotta be even. 260. Yeah, no, it's okay. Oh, that's just like the radius. So the only thing, as long as they're both even, all that happens is you get closer to being a square. So like, let's see how they're kind of a little less rounded off on the corners. So like if we go to the 100th, I know. 100. Yeah, it almost looks like a square. Right? It's not. No, you got rounded corners. They're not 90 degrees. So. And then the 16 just changes this. Anyway, okay, so first if we want to find y double prime, we need to find y prime first. So we'll do that implicitly here. taking the derivative of x to the fourth, it's not too bad. That's just 4x, 4x to the third. And when we do the y, we're just remembering that y is a function of x, so we'll have 4y to the third, but then times dy dx or y prime, whichever one you want to call it. I guess I'll call it y prime here since I have it labeled that way. And then on the other side, there's just 0. Yeah, that's not too bad. And then we want to solve for y prime. So 4y to the third y prime is negative 4x to the third. And then what can we do? Divide by 4y to the third. Those go away. Our 4's cancel. So end up with negative x to the third over y to the third. There's our first derivative. Okay. So keep track of that. So then to take the second derivative, how do you, just in general, how do you find the second derivative of a function? You take the derivative of the derivative. Right? So now we'll just take the derivative of negative x cubed over y cubed. So to do that, unfortunately, I have to use what property? Quotient rule. Yeah, quotient rule. So let's see, derivative of the first one, so negative 3x squared, or the top, let's say first, times the bottom, y cubed, minus the top one, times the derivative of the bottom. So on that one, we get 3y squared y prime, over the bottom squared, thinking ahead there. Now let's just simplify this a little bit. Let's see, it's 3x squared y cubed, and then that's plus 3x cubed y squared y prime over y to the 6th. Okay. The only thing that's a little bit weird here is that we've got this y prime. We're trying to find y double prime, so we don't want a y prime in our answer. So y prime, though, we know what it is. We've got an explicit formula for it. Now, y prime, we said, was negative x cubed over y to the third. Okay. So let me change how I've got this written a little bit. That y prime was in the top, so well, I can't do that because it's, hang on, I'm trying to get too cute. Sorry. Y prime. So what do we substitute? And if we just want to like evaluate, find the numerical value of the second derivative somewhere, that's fine. But Let's see what we can do. We can clean that up some, right? So y squared and y to the third. We can simplify. Right? I'll leave this one y there. So let's see where that gets us. That gets us to let's make that a minus x to the 6th over y, and then y to the 6th. The other route. That may or may not be all we can do to it, but not bad. If I find something I messed up on, we'll fix it next time. I won't make you sit here and let me look at it. That might be. That's the idea, though. That's the idea. All right. Questions on those? Oh, just.
So when you were trying to find why
Mm-hmm.
did you do
The quote.
why did you do
I got you. So I did, right, because here we still have a y. Right, so y is still a function of x. So we had to keep going there, yeah. If we had gotten it down and it was all x's, then we'd been okay, yeah.